Here is the first example on the Jordan form. Find the state and output equation for the following mathematical equation by using Jordan form. Okay, so here to convert this into mathematical equation, Jordan form is nothing but we're going to convert the given time domain equation into S domain equation. That S domain is nothing but Laplace domain, also called frequency domain. So we know that y dot is nothing but dy by dt in time domain. When it comes to S domain, that y dot we can replace that with s times y. Okay, so if I use the S terminology or Laplace transformation, you will end up with s squared times y plus 3s times y plus 2y equal to u. Okay, so if I write it down in S domain, this is the transfer function y by u equal to 1 over s squared plus 3s plus 2. So it's a kind of perfect square, so it's going to be s plus 1 times s plus 2. If not, you may end up with complex poles basically. So by using partial fraction, I'm converting this into or dividing into two individual terms. One is a over s plus 1 plus b over s plus 2. To find a and b, I'm going to use the substitution method. To find a equal to take the whole equation other than the denominator of a. So 1 over the whole equation is s plus 1 times s plus 2, but other than s plus denominator of a, so eliminate s plus 1, so we'll end up to 1 over s plus 2 and substitute s equal to minus 1. If I substitute that, I end up with a equal to 1 and b equal to same thing, take the whole equation other than the denominator of b and substitute b equal to or s equal to minus 2. I end up with b equal to minus 1. Now I have y by u equal to two individual terms. One is 1 over s plus 1 minus 1 over s plus 2. Now we have to draw the simulation diagram. How to draw the simulation diagram? In the previous case, we use integrators. So if you have y dot passing through the integrator, you will end up getting y. Here, instead of integrator, we will use 1 over s. So s times y is passing through the 1 over s. You will end up with y output. Now I'm going to draw a simple simulation diagram. Okay, this is simple feedback simulation diagram. Y as an output, u as an input. Okay, so to get sy equal to u minus f times y. The signal here is y, so whatever coming here, it must be fy. So sy equal to u minus fy. So if I pull the fy to the other side, sy plus fy, take out the y, it's going to be s plus f. So y by u equal to 1 over s plus f. So if you have 1 over s plus f, this is a simple simulation diagram. Now I have 1 over s plus 1. So here f is nothing but 1. In the other case, f is nothing but 2. So I'm going to draw two individual simulation diagrams. So those individual simulation diagrams are right here. Okay, so 1 over s and s plus 1, so the feedback is only 1, so unity feedback. Okay, in the other case, 1 over s plus 2, so the feedback is 2. Okay, so remember, if you have plus 2, the feedback is going to be minus. If you have minus 2, feedback is going to be positive. Now I'm subtracting one another, so basically u as my input, y as my output. To get y, I'm going to add, this is positive, the second case is negative. Okay, I'm adding that. So subtracting those two. So y is nothing but we are adding here both of them. What I can do, I can use these signs to the other side. Here both of them are unity, so it might be a little difficult to explain here. I will explain it in the next example. Time being, you can take this positive and negative signs either input side or output side. Okay, so now I'm going to define x1 and x2. So x1 dot is nothing but minus x1 plus u, and x2 dot is nothing but minus 2x2 minus u. Okay, y equal to x plus x1 plus x2. So a is nothing but minus 1, 0, 0 minus 2, b is nothing but 1 minus 1, c is nothing but 1, 1, d equal to 0. This is our first example. I'm going to go over the next example. So find the state and output equation by using Jordan form. Okay, here y double dot minus y dot plus 6y equal to u dot minus u. So it's s square minus 5s plus 6 times y equal to s minus 1 times u. So y by u is nothing but we will end up with s minus 1 over s square minus 5s plus 6. It's a perfect square. I end up with the poles s minus 2 and s minus 3. By the way, this denominator, so this denominator is called characteristic polynomial. Okay, we call that as characteristic polynomial. Okay, now if I make that equal to 0, then we call it as characteristic polynomial equation. That characteristic polynomial equation will give us the poles of that system. Okay, so what is the advantage of poles? We'll talk in the future chapters. Poles will define whether that system is stable or not. So based on, so poles are important for any system. So are we building the stable system or not? We can find out by using this mathematical equation. Now, so again, I'm going to do the partial fraction s minus 1 over s minus 2 times s minus 3. So to find a, take the whole equation other than the denominator of a, substitute s equal to plus 2. So I end up with minus 1 a value and b value as I end up with 2. So this y by u is nothing but I end up with minus 1 over s minus 2 plus 2 over s minus 3. Okay, now I'm going to build, this is nothing but, this simulation diagram is nothing but 1 over s minus 2. Okay, since I have minus there, when I draw the simulation diagram, that's going to be positive. Okay, now the second part is 2 over s minus 3. I will talk about 2 later on, but I'm going to draw simulation diagram for 1 over s minus 3. So here is the simulation diagram which tells us 1 over s minus 3. Since there is a negative here, I will end up with positive there. Now, as I mentioned, this negative 1 and positive 2, you can connect them at the output side or you can connect them at the input side. In this example, I showed both. Okay, so the first case I did it at the output side, so minus is right here and plus 2, I added plus 2 to the output side. Okay, now my y is nothing but, so if I take the two state variables x1 and x2, here is my x1, here is my x2, y equal to minus x1 plus 2x2, and x1 dot is nothing but 2x1 plus u, x2 dot is nothing but 3x2 plus u. So my A matrix 2 0 0 3, b is 1 1, c is minus 1 2, d equal to 0. Now if I do it on the other side, so my output side is just direct addition, but look at here, minus 1 came here, so it doesn't matter whether you add that there or you add it right there, and those two indicates the same thing. Okay, either just adding, saying that's a minus signal coming there, or we can say put minus 1 there and say positive signal is coming over there. Is both of them are the same things. Okay, now my x1 dot is nothing but I end up with 2x1 minus u, and x2 dot is nothing but 3x2 plus 2u, y equal to x1 plus x2. So the previous case and this case, the only difference is you can clearly see A matrix is same, but B and C are interchanged based on where I connect my the numerators. Okay, so basically in the future classes we'll learn about controllability, observability. So one of them is useful for controllability, one of them is useful for observability. Okay, I'll stop this video here. I'll continue with more examples in the next video. Thank you.